Okay, all right, good. Okay, all right. So let me just continue from where I left off yesterday. Just to remind you, yesterday I was telling you that I was just talking about scanning tunneling microscopy and quasi-particle interference, and I showed you how we can obtain information on the dispersion of any kind of two-dimensional state, right? These can be quasi-two-dimensional states of the bulk or even surface states. And I gave you an example of topological crystalline insulators and showed you how we can obtain dispersion. I also showed you how we can actually see beautifully what the Fermi surface is doing as a function of energy. And in this particular case, I showed you how you can visualize a Lifshitz transition. In any case, so as I said, this is energy versus momentum, and you can see in this topological crystalline insulator, you get this kind of a dispersion, but we're not able to go all the way to the Dirac point due to various reasons. And in order to actually get more information, there is a very, very nice technique called Landau level spectroscopy, and that's what I'd like to describe very quickly, because I really want to get actually to an experiment talking about, Marana fermions in this kind of system where you have superconductors with a pi phase shift. I want to try to get to that, so let me actually talk about this quickly. Okay, so let's say you turn on a magnetic field. Oh, this doesn't work. Okay. You turn on a magnetic field, and you're all familiar with this. You can actually very nicely figure out the effect of a magnetic field on electrons by looking at by taking a semi-classical approach, which is the Onsagar quantization condition. So the condition is that in real space, the area of the cyclotron orbit encloses an integer number of flux lines, right? So you can go to area and real space, from an area in real space to area and momentum space quite easily using the magnetic length. And if you do that, you get that the Landau level area in K space, which is pi k squared, should be equal to this quantity, where gamma is a phase, which includes two contributions. One is the Berry's phase, and the other is called Maslow phase, which is just a half. Okay, so just using this simple condition, you can actually derive what you expect to see when you turn on a magnetic field for different kinds of two-dimensional electron gases. For example, you can tell what you should expect for something that has parabolic dispersion, and then you can contrast that with the topological surface states, which are expected to have linear dispersion. So let's start with electrons that are like normal electrons where the energy goes as k squared. And in this case, Berry's phase is 0. This is 0. So this gamma is equal to half right here, right? And so the Landau level spectrum, right, when you turn on a field, the energies fall into these Landau levels. The Landau level spectrum looks like this. So the things to notice here are the following. The energy of the Landau level, right, the energy spacing is linear in magnetic field, and the difference between each Landau levels is a constant. So that's the spectrum for a regular conventional electron gas. And now if you go to Dirac surface states, you have a pi Berry's phase, and that gives you a gamma of 0, right, this gamma of 0. And also, you know that the dispersion goes as k. So if you put all these together, you get this expression for the Landau levels. Now the Landau level separation goes as square root of NB. So these two are very different from one another. And another big difference between these two is for Dirac surface states, you get one Landau level at the Dirac crossing, whose energy doesn't change with magnetic field. Okay, so these are the differences. And now let's just visualize this. So if you look at the spectrum for Dirac dispersion, you get these unequally spaced Landau levels, whereas for just a normal non-relativistic band, you get equally spaced Landau levels. And in addition, you're always going to get one non-dispersing Landau level at the Dirac point. Okay, So this is really beautiful because this will allow you to distinguish between something that looks like a Dirac spectrum and something that disperses in a parabolic way. The other interesting thing is that if you take a Dirac spectrum and break the symmetry that protects this Dirac point, let's say it's time reversal symmetry, you turn on, you have magnetic impurities, or if it's, in this particular case, it's mirror symmetry, right, for topological crystalline insulators. So if I break mirror symmetry, then the Dirac electrons acquire a mass, and in that case, you can ask what happens to the Landau level spectrum. And of course, it turns out that you get the same spectrum at high energies, far away from this mass gap, but at low energies, you still actually get one non-dispersing Landau level, and this one non-dispersing Landau level lies either at the top of this band or the bottom of this band, depending on the sign of the mass. Okay? All right. So what do? We turn on a magnetic field. In STM, we can measure density of states, like I told you. So if you go from this kind of dispersion to these discrete states, then what you should see in STM is actually peaks at the positions of these states as a function of energy. So we can find all the peak positions and plot them as a function of square root NB. And very quickly, why square root NB? That's because square root NB actually represents the momentum at that particular energy. So plotting the energy versus square root NB is exactly like plotting E versus K without the Landau level. So what you do is you can do that, plot energy versus square root NB for different magnetic fields, connect them together, and you'll get the dispersion without a field. Yes?
How do you know where is N0?
How do you know? This is the only one that will not change with field. So the thing is, that's why you need to do a magnetic field dependence. Okay? When you do a magnetic field dependence, every other Landau level will change, but this one will not. Okay, so let's actually look at data. Here's a Didv spectrum without the field. I showed you this yesterday. These are the Van Hove singularities. Now you turn on a magnetic field, and you can see, this is amazing. You can actually see peaks, and each peak is a Landau level. Okay. Now in this particular case, we know that this minimum is the Dirac point, but let's just look at what happens as a function of field. By the way, this is just showing you what we did. We took a line cut, and we averaged all the spectra. So the spectrum here that you see actually is a derivative of the spectrum, and you pick up all the peaks really nicely when you take a derivative. Okay. So now let's look at the actual raw data. So here's magnetic field dependence, and each of these little peaks is a Landau level. This is as a function of magnetic field, as I said. You can see that there's a peak right at the Dirac point, which actually doesn't change as a function of magnetic field. Its energy remains a constant. You can see it nicely here. This is that peak. Its energy actually doesn't change. And all of these other peaks, their energies change as a function of magnetic field. Okay? So you can plot all this as, so this is energy on the y-axis. This is square root NB, as I said. And these are all the points that I picked up from these spectra. And what you notice is something very nice. First, there is a peak right at the Dirac point, and it's this one, and it doesn't change with field, so that's exactly the Dirac point. All of these other peaks come from all the other magnetic fields that I imposed, and if you connect them all together, you get an amazing, beautiful Dirac dispersion. Okay? But more interestingly, you get two other points on either side of the Dirac point, which also don't disperse very much with magnetic field. And the question we have is, what is this? And as it turns out, the answer is the following. So here are those two other peaks that don't change with field. The answer is that in order to get these peaks, what you have to do is you have to give a mask to the Dirac electrons. So the question is, how do you provide a mass to these Dirac electrons? And the way you do it in this system is by breaking mirror symmetry. So let me just actually, since I want to get to the next part of the talk, let me just quickly tell you this. So the scenario in this case is, remember, you have a topological crystalline insulator. You start with 4 Dirac cones. This is the crystal structure. Remember, we have 2 interpenetrating lattices, the lead lattice and the selenium lattice. If you were to have a distortion where you move one of the lattices, right? So these are the red dots. You move them in one direction, let's say this way, and you move the other one in the opposite direction, then you get a kind of a distortion which breaks mirror symmetry in one direction. In this direction, mirror symmetry is broken. This doesn't have a partner, for example, whereas mirror symmetry is preserved in this direction. In that case, what you would find is that 2 of the Dirac cones get gapped out, whereas 2 of the other 2 don't. Okay. Now let's see what. So that's our conjecture. And in that case, what you would find is that you would get a coexistence of massless Dirac fermions and massive Dirac fermions, and that would explain the spectrum that we see. And the question is, do we have any proof for this? And so, as I said, at low energies, you don't see both lattices. But as it turns out, at high energies, you can see both lattices. And let me just go through this very quickly. There's Fourier transform that can tell you that this kind of symmetry is being broken. But I can just take this kind of an image and do something that clears up this image. And this is called average unit cell. And you can immediately see this kind of zigzag pattern where mirror symmetry is actually broken in this direction, right? It's preserved in this direction, and it's broken in this direction. Okay, so all right, so this is what we saw, and that's really nice. And now, in the next few minutes, before I jump into topological superconductors, let me show you what happens as you tune the system from a topological state to a trivial state, and something quite interesting happens. Okay, so we did the same thing. What we did was we changed the tin content, and as you change the tin content, you go from the topological to the trivial phase. So you can use Landau level spectroscopy to track what the surface states do as you go through this phase transition. So you remember the gap has to close and reopen, okay, the bulk band gap. When the bulk band gap closes, these surface states actually get crushed together, like in this fashion. More interestingly, remember the surface state penetration depth right at this critical point should go to infinity. And we should see evidence of that in our data. So let's see what happens. So, yeah?
What's this temperature axis? I'm not used to seeing temperature like 200 Kelvin. So how does the temperature affect the phase transition?
Oh, so in these topological crystalline insulators, there is actually a topological to trivial phase transition as a function of temperature, as it turns out. So I have asked this question. We did this a while ago, and I've been thinking about this. There is a small distortion, like the small change of the lattice parameters. I don't know. In some semiconductors, that does change the gap. So this means that the gap, high energy gap, high temperature gap, must close and reopen as a function of temperature. And that could just be because of the small change in lattice parameters. I'm not exactly sure what it is.
Your measurements are presumably...
My measurements are not like this. Mine are at low temperatures just by changing the tin content. Yeah. ARPAS has done this. Yeah. Yeah?
About the red distortion, do you have an explanation why?
Yes, there is so basically the end member of this thing is actually orthorhombic. And if you look at the surface of that orthorhombic crystal, then it looks like our distorted crystal. So the system has a tendency to go in that direction. I will show you that what we believe is happening for these particular compositions is it's not that the bulk is distorted. We know the bulk is rock salt, actually. That is known from X-ray measurements. This is happening, this distortion I talked about is happening only on the surface. And you'll see evidence for that when I show you what happens during this transition. Yeah, uh-huh.
Could you show the plot again of all these DIDV lines where
Yeah.
you identified the peaks?
Yeah.
Could you show this?
Sure, of course. Yeah.
Because I mean, in principle, for each lambda level that you show, the contribution to the density of states should be the same for each lambda level you pass, right? The height of the peaks kind of changed.
Oh, oops, I have to go really far back. Hang on for 1 second. No, just a second. You mean here?
Yeah.
You mean,
Each lambda level has like a fixed number of states, right?
yeah, okay, there is a sort of a background that you have to subtract. So we did think about this. There's some, okay, so there are two things going on. One is there's height and there's width. And so, who's asking me this? Sorry, you are, yeah. There's height and there's width, and the integrated area has to be the same. And the width is determined by, any kind of disorder or inhomogeneity in the system. So there is that. And the second is to actually look at that carefully. We did notice that, look, these things are riding on top of some background. And you have to think about that background as well. And so what's happening is that each Landau level, they're closely spaced, so they actually overlap each other. And so when they overlap, so what you're seeing with your eye is not the full Landau level peak. You're seeing a bunch of overlapping peaks, really. Yeah. So that's what gives you the background also. Yeah. Yeah, sure.
Just when you had the Dirac dispersion, the beautiful plot,
Yeah.
there seems to be some kind of a discontinuity between the points of 40. Is this just because they're different measurements and they don't match up, or is there?
Just 1 second. Let me pull that up again. Right here.
Yeah.
This one?
Yeah.
Oh, this is the Lifshitz transition.
Ah, okay.
So at the Lifshitz transition, where the bands on either side merge together, then you actually should have a jump in the area. This is expected. And in fact, if we can fit this really beautifully. The area should go double at that point.
It's kind of when you have those two circles
And they merge together.
they merge together, so
So suddenly the electrons have a bigger K-space area.
and the merged circle is not exactly the same as the combined two circles.
No, because the two circles have a smaller area than the merged circle. So there's a sudden jump right at the Lifshitz transition.
Okay, thank you.
Yeah. Okay. So now let's actually ask what happens as a function. Let's ask when we do this topological to trivial. So here's the topological phase. This is the data I showed you. And then, this is also topological. This is this one. And now let's go to the, I'll plot the dispersion in a second. This is the critical point. Now look, these two topological phases, you have the Dirac point, you have the two side things which represent the mass, and same here, Dirac point, the side things that have the mass. Right at the critical phase, there is something small going on. There's still something that looks like a Dirac point, right? And then, whereas you don't see the two mass peaks very well here, and then at the trivial, in the trivial phase, the first question is, do you even have a surface state, right? And the answer is yes. Look, you still have Landau levels, but notice there is no peak at the Dirac point. There is a complete absence of a peak at the Dirac point. So already you realize that the trivial phase dispersion should look completely different from the Dirac dispersion on the topological side. Okay? So now let's plot the dispersion. Yeah, is this okay? Yes. Yeah? Okay, look, this is amazing. So this is the evolution of the band structure as you go from the topological to the trivial phase. So here are, we're looking very close to the Dirac point, so we have just a few points here. But you have the Dirac point here, and then you have these 2 points. You can actually draw these straight lines. And then this is the critical composition. At the critical composition, you still have those 2 cones merging into one another, and you still have this Dirac point. And on the trivial side, the surface states now, they're no longer Dirac-like, they're actually Rashba. So you have, on the trivial side, you have a pair of Rashba split bands, okay? And the thing that I want to say here is that this data, there is no other way to fit this data except the way we fit it. The reason is that the magnetic field dependence imposes a very strong constraint on these fittings. So this is the only way we can fit this data. No Dirac point, Rashba split bands. Very interesting that this is how the system goes from the topological. So this is what is happening. In the topological phase, you have these 2 bands on either topological bands on either side of that Brillouin zone boundary. And then as you dope towards the trivial side, these cones merge together. And on the trivial side, you end up with this band structure. Yes?
Yeah, why can you only see one of the logical directions? You have points that just have certain energy on the outer band, and then you get the inner.
That's just because, it's just a resolution thing. These things are so close together that we're not able to resolve them. Yeah.
So is the Rashba surface state a result of this low doping level causing structural inversion symmetry, or is there another mechanism?
So why do we see surface states?
At low doping. No, why do we see the Rashba at low doping only?
Oh, there is. So it's so you don't have, in the topological phase, you just have the topological surface states. In the trivial phase, you don't need to get this. You don't need to get surface states. You could have had nothing, for example. This system just happens to have surface states.
Is there also Rashba in the bulk?
Let me answer it this way. The system has strong spin-orbit coupling. Okay? And so the strong spin-orbit coupling leads to this kind of a surface state. This happens even in gold, for example. So in gold, there's a surface state, there's strong spin-orbit coupling, and you see that the surface plates have split due to that strong spin-orbit coupling. Okay? All right. So this is how the phase transition occurs. Then we did something else. We tracked the mass. Remember this mass? This mass term, how big is this gap? We tracked that as a function of doping, right, tin concentration. And what you find is that this delta, this mass term, actually decreases as a function of composition. So the question is, why does this mass decrease, right? And one possibility is that the distortion itself might be changing as a function of tin concentration. And we checked that, and it turns out that the distortion actually remains pretty static as the tin concentration changes. So then why does the mass decrease? And I'll cut to the chase because, again, lack of time. The answer is very simple. It's because the surface state penetration depth is changing. So as you go from the topological to the trivial phase, the gap is getting smaller, and as the gap is getting smaller, the surface state penetrates more and more into the bulk. And in fact, at the critical composition, the penetration goes to infinity. That means that the amount of the surface state that's able to sample this distortion, which happens only on the surface, gets smaller and smaller, and that's why the mass goes to 0 at the critical point. Okay, so that's it. That's all I wanted to say. Unless you have more questions, I'm going to actually do a complete shift and talk about topological superconductivity. Any other questions about this? Okay, good. How much time do I have? 30 minutes, okay. Okay, so some of the stuff has been covered by a lot of the talks that you heard over the last week. So I'm not going to talk about the theory in great detail. So let me just quickly remind you of one thing, though. So one question is, how do you construct a Majorana fermion? And you've seen the answer to this question. Really, the reason you want to use the superconductor is that the excitations of a superconductor are Bogoliubov quasiparticles, which are naturally particle-hole symmetric. They are combinations of electrons and holes, right? This is a Bogoliubov quasiparticle. It is partly an electron and partly a hole. And that, therefore, it's a neutral entity. So it's particle-hole symmetric and a neutral entity. So it's clearly the thing that you want to use when you want to create a Majorana fermion. So one thing you have to realize is that if you have an S-wave superconductor where spin is a good degree of freedom, then your Bogoliubov quasiparticles have little arrows here which have the spin degree of freedom in it. And so if you want your creation and annihilation operators for these Majorana fermions to be the same, you have a problem, which is that the spin degrees of freedom don't cooperate. So the spins are actually flipped if you want this to be equal to this. So what you want to do is basically get rid of these little arrows, and there are multiple ways to do that. One way to do it is to actually look for triplet superconductors. Triplet superconductors have equal spin pairing, and then you don't have to, the Bogoliubov quasiparticle excitations, you don't have to write down the little spin quantum number anymore. And so in a triplet superconductor, the low energy excitations naturally look like Majorana fermions. The other way to do it is what many people have talked about already, including Adi today, where you take a semiconductor with strong Rashba coupling such that you have this kind of band structure, and then you turn on a magnetic field and you gap out this point, right? You gap out this crossing, and now if you were able to put your Fermi energy here, then you have, because of spin-orbit coupling, you have a sort of spin momentum locking, and only one band crossing the Fermi energy. And in this case, this combination of things gives you the kind of Majorana quasiparticles that you need. Bogoliubov quasiparticles that you need. The third thing is to use topological superconductors. So I'm not, all this. So here's the prediction for a topological superconductor. So if you have a topological insulator and you put a superconductor on top, then there are two scenarios in which you can get Majorana fermions. One is if you turn on a magnetic field, then in the vortex cores, so what's happening here is that the surface state of the topological insulator is proximatized by the superconductor to become superconducting. And then when you turn on a magnetic field and you look in the vortex cores, you'll see Majorana bound states inside the vortex cores. The other way is, which Adi was talking about, which is you take a topological insulator, you put superconductors with a pi phase shift, and right at this interface, what you get in this case, remember there's no magnetic field here, you don't need a magnetic field. Even without a magnetic field, what you would get at this interface is one-dimensional propagating Majorana fermions. So these are not bound states, these are actually propagating states, just like Jason talked about the other day, okay? So what we'd like to do is to actually look at the scenario, and what we expect to see is, if we could realize the scenario, we would expect to see in a Didv spectrum a sharp peak right at the Fermi energy inside the vortex core. Okay, so now let me show you the experiment. This experiment was not done by slapping a superconductor on top of a topological insulator. Instead, we found, it was realized quite a few years ago in 2015, that iron, selenium, tellurium, for a range of compositions, is topologically non-trivial. So iron FeSCTe is actually a well-known superconductor. It's an S-wave superconductor. That's what you need. However, it turns out that for some range of selenium compositions, this S-wave superconductor is also topologically non-trivial, meaning that it has non-trivial surface states. So in one material, you have a situation where you have both an S-wave superconductor as well as on the top you have these topological surface states, which are of course going to be gapped out due to proximity effect. So this is a great system in which to realize Majorana fermions. You turn on a magnetic field and you look inside the vortex cores, and hopefully you see a zero bias state. Okay, so let's first do that, right? And let me not just go into that. Okay, let me just show you this for a second. This is the crystal structure of this compound. There's a reason I'm showing you this. So this is a layered compound. You have a layer of iron atoms sandwiched by 2 layers of selenium atoms. But the top selenium row and the bottom selenium row are shifted with respect to one another. You can see that. And so this is a top view showing all 3 layers, right? And so one set of these atoms is the top selenium, the other set of these is the bottom selenium, and these are the iron atoms. Okay, so this is a crystal structure. One thing I want to point out that in a given crystal, right, which is let's say this is the top selenium, whether these top seleniums occupy this position or the equivalent position here, is a choice made by the crystal. So you can imagine that in a given crystal, you might have areas that look like this and areas where this is entirely flipped upside down, okay? So that'll give you a domain wall. All right, so this is what the band structure looks like. This is very much the same for any iron-based superconductor. You have these hole pockets at the gamma point and electron pockets at the M points. And actually, in 2018, ARPES studies, this is ARPES data. You can see this is the bulk band, and up here is also some bulk band. But then inside the gap, you see these linearly dispersing states. These are surface states. So there seems to be ARPES indication that this is indeed topologically non-trivial. Okay, now let's look at what happens when you turn on a magnetic field. Okay. By the way, just as an aside, the quality of these samples is really important. If you have samples with a lot of iron, then, sorry about that. If you have samples with lots of iron, then the superconducting gap looks like this. Look how shallow it is. And look, it doesn't even go, not that only that it doesn't go to 0, these coherence peaks are very broad. Now let's look at a really nice sample with very little iron defect. And this is what the sample looks like, no iron defects. And now look at the gap. It's really beautiful. You have a beautiful S-wave gap, okay? And you have multiple coherence peaks. And these coherence peaks, the reason you have multiple coherence peaks is because you have all of these pockets. You have these electron pockets and the hole pockets. Each pocket has a slightly different gap. And that's why you see these multiple coherence peaks. Okay, so I'm going to just breeze past all the stuff having to do with these gaps and talk about vortices. So now we turn on a magnetic field, and this is a vortex plot in the bad sample, and this is a vortex plot in the good sample. There's too much light, but really. Let me see if I can turn off this light. Okay, it's still not very clear, but in any case, don't fall asleep. So in any case, each of these bright dots is a vortex. Okay, so this is a Didv map Didv map at 0 bias. And typically, if you didn't have a magnetic field turned on, at 0 bias, you have no density of states. It should be completely black. However, when you turn on a magnetic field, you get these states inside the gap, and that's how you find these vortices by taking a Didv map at 0 bias. So if you take a line cut through one of these vortices, you see this zero bias peak. And of course, it's a big problem. You don't know whether these zero bias peaks are actually Majorana fermions, or if they're normal Caroly-Dejean states, which should also occur inside vortex cores. Yes?
Do the vortices form like a triangular, or like what kind
Yeah, yeah, they are triangular lattice. Sometimes the lattice is slightly distorted because sometimes the vortices get pinned to impurities and defects, but it is a pretty decent triangular lattice in this system.
You can see the triangular lattice formation quite
Yeah,
easily.
you can see the triangular lattice formation.
Okay, thank you.
Yeah. It depends on how many defects you have. Yeah. Okay. So the question is, how do you know this is a Majorana fermion and not a Caroly-Dejean state, which should also be there? Okay. So you can actually ask a question about numbers, right? So let me answer that question in the following way. So the Caroly-Dejean states should, the energy difference between them goes like this. It's delta squared over EF. Now, I didn't tell you this, but the gap in this, on the surface state gap is about 1.5 milli-electron volts. The Fermi energy, as it turns out for the surface state, it's pretty shallow, so the Fermi energy is only about 10 MeV. So these Caroly-Dejean states are expected to be 100 microvolts space. So this spacing should be 100 microvolts. So we didn't do this work. This work was done by Hanaguri in Japan, in Riken. They did some very, very, very careful measurements at very low temperatures. I think about 40 millikelvin, right? And their resolution was really very, very good. And what they were able to show is that they see a zero bias peak, right? This is zero. And then this next state right here, so this next state is actually at 100 millivolts. So they can see the difference between something at 0 and something at 100. And they were able to show that within their resolution of some, let's say, 30 microvolts or something, this zero bias peak is exactly at 0. Okay? So by the way, the resolution does tells you whether you're able to distinguish two peaks that are separated by that amount. This thing being at 0 is even better than that resolution. Okay. So they were also able to show that as you increase the magnetic field, you get all of these states inside the vortex core, but the zero bias peak actually diminishes and then goes away at higher magnetic fields. And this is not completely understood, but this might be due to the interactions between these Majorana fermions. Yes?
So I'm wondering whether the occurrence of these zero bias peaks are correlated with the topography or something of the sample that could say maybe they are related with defects or something.
So this is what, this paper is really beautiful. I would urge you to look at it. They did very, very careful studies. It's STM. You know where all the defects are. You go to those positions where you see these vortices and look at zero field and ask, is there a defect there? And if there's no defect, you're good to go, right? So what they found was at very low magnetic fields of not very low, of fields like 1 Tesla, 80% of the vortices showed zero bias peaks, okay? And then as you increase the magnetic field, the number of vortices that show zero bias peaks goes down. That's why in the first study, only 30% of the vortices showed zero bias peaks, because they were looking at higher fields. In any case, yeah?
It looked from your earlier slide that there were 2 gaps.
There are multiple gaps.
Or several gaps.
Yeah.
Does this have an effect?
Yeah, so there is the surface state that has a particular gap. And
there's only one?
only one gap.
So the multiple gaps are only in the bulk?
The bulk gaps are also seen by us. So the thing that I skipped over was an analysis of which gap belonged to which state. So there are the hole-like bands and the electron-like bands. There are 2 hole-like bands. Those give you 2 gaps. Actually, they're different. We've known that for a while from ARPES. Then the electron band has its own gap, And then the surface state has a particular gap. And that surface state gap is about a 1.2, 1.5 millivolts. Yeah. Yes?
Is this basically just because if you increase magnetic field, you increase the number of vortices?
You increase, the
vortices.
separation decreases and the inter-vortex interaction might increase. Yeah, this,
You have so many vortices that then the Majorana kind
this is, but this is, there's no, I don't know if there's a good theoretical understanding of exactly how fast this goes down, but you know, that might be an explanation, yeah. Okay, so in the last few minutes, what I'd like to show you, how much time do I have? Okay, good. Okay, that's good. That's enough. So let me just recap the vortex data. You know, multiple groups have seen these vortex bound states. Normally, in regular systems, it's really hard to distinguish. It's really hard to distinguish between a Majorana bound state, which is supposed to occur at zero bias, and the regular Curry-Dejean metricon bound states, which also happen inside the vortex cores, because they all get bunched together. But in this system, because of the parameters that we have, which is delta and EF, the Curry-Dejean metricon states are actually quite well separated from the Fermi energy, 100 microvolts. This allows you to resolve that state at zero bias very clearly just by itself, right? And so you shouldn't really see a zero bias state. The Curry-Dejean states are always separated from the Fermi energy by some energy. And so the existence of that zero bias state, as well as I haven't shown you this data, you can actually see in certain vortex cores, there are also other additional states which have the same Marana character that are separated from the zero bias state by a different integer spacing. So the existence of those integer space states, all that put together strongly suggests that in this system at least, the zero bias state is actually a Majorana fermion. Okay, again, like Charlie was saying, strongly suggests, you can hear my words, right? Strongly suggests, I'm not saying it's smoking gun proof. Okay. Okay, now what I want to show you next is this thing that we've been hearing about all week, which is, what if you had a topological insulator and you put two superconductors on top with a pi phase shift between them? And what if you looked at this boundary? You would, in theory, you would see propagating Marana fermions. And what I'm going to show you is that we didn't have to do all this. It turns out that in this system, due to a quirk of fate, you actually get this for free, right? Let me show you that now in the next few minutes. Okay. So this material, FESCTE, it was predicted in 2013 by Jiangping Hu. And in fact, a lot of people have been talking about this recently. The order parameter, these pluses and minuses represent the phase of the superconducting order parameter. It so happens in the system that the phase of the order parameter actually changes. These are the iron atoms here. These are the selenium atoms on top, and these are the selenium atoms underneath. The phase is actually changes from the top selenium layer to the bottom selenium. There's actually a superconducting, the order parameter has a phase shift. So what then you can ask the question, so like I told you before, you know, the positions of these top seleniums and the bottom seleniums, this is from a different angle, but they're actually shifted with respect to one another. You could imagine a situation like a domain wall where this gets flipped, okay? And if that happens, then at that interface between these two regions, you would have a pi phase shift of the superconducting order parameter on your surface. So you can go looking for those kinds of domain walls. So this is a representation. This is a top view. So on the left side, you can see these are the top selenium atoms. and then on the right side there's a phase shift. Okay, so there's and in between those two should be a domain wall. Okay, so these are really lovely samples. So a lot of our surfaces look like this, right? But then you can go searching and you can find regions that also look like this. And not all of these things are the kind of domain wall that we're looking for. But if you go searching, you can find, this is not, something is, okay, doesn't matter. So you can't see this clearly, but these little dots are the atoms. This is the domain wall. And if you zoom into the domain wall, what you see is that, first let me show you the Fourier transform. Already from the Fourier transform, you see the splitting of the peaks. That already tells you that this side and this side actually have some kind of a shift in the lattice between them. That's what the splitting tells you in the Fourier transform. And now if you zoom into the domain wall and you track the positions of the selenium atoms from one side to the other, you can see that the selenium atoms on this side are actually shifted from the selenium atoms on this side by half a unit cell. And so this half a unit cell phase shift is what you expect when you have this flipping of this whole crystal, right? And now you can, okay, I don't want to do all this analysis. Now you can ask, what do you expect to see? So if you go to some random impurity in the system and do a spectrum, what you see usually are bound states inside the gap. So you see these sharp peaks. Interestingly, these sharp peaks are at 0. This is, for example, an ion defect. Also gives you zero bias peaks, by the way. So you should be, the question someone asked about, hey, you see these zero bias peaks inside the vortex cores, are they due to impurities, is actually a really good question, because any impurity in the system, which is an ion defect, also gives you a beautiful zero bias peak. In any case, so you get these kinds of peaks, or if it's some other random impurity, you can get these split peaks. You can get all kinds of things inside the gap. So let's see what we see when we go into that domain wall. Yes? It should. It doesn't.
Oh, but it can.
It can be. So where this scattering state is depends on the strength of the scatterer. So for a very, very strong scatterer, you end up getting a peak at zero bias. Yeah. It's a Shiba state. Yeah. Yeah. These are S-wave superconductors. These are S-wave superconductors, and if you put magnetic impurities, you get Shiba states inside the gap. And so that's what they look like. So this is just an example of what impurities and defects do. And now let me show you what you see on the domain wall. So on the domain wall, we were actually surprised when we saw this. So what we see on the domain wall is a sort of a uniform increase in the density of states. No peaks, nothing, just a uniform increase in the density of states. That means you have states filling up this entire gap, okay? I'd never seen anything like, we've been studying superconductors for, more than a decade, and we'd never seen anything like this. And so we were really puzzled. And so then, as you take a line cut across this domain wall, so if you go in this direction, you see the nice gap. So this is density of states plotted as a color plot. These intensities, higher intensities, are due to the coherence peaks. It's black here. There's no density of states. If you go along the domain wall, you see basically the gap gets filled uniformly along the domain wall. Okay, and then let's do some temperature dependence to see if there's something about the domain wall that's different. So at high temperatures, at 14 Kelvin, both spectra away from the domain wall and on the domain wall look pretty much the same. There's no difference between them. And then so here's a spectrum on the domain wall compared to the spectrum, at 1.7 Kelvin and 14 Kelvin. By the way, TC is about 12 Kelvin, okay? So you can see that at 14 Kelvin, this is a spectrum on the domain wall. At 1.7 Kelvin below TC, this is the spectrum on the domain wall. So this is clearly connected to superconductivity. So the question is, what is this? How do we understand this uniform filling of the gap? Then you can ask, what do you get if there's a pi phase shift? And we know the answer already. What you expect to see if you have a pi phase shift is propagating states, Majorana states, inside that fill up the gap. These are linearly dispersing. And so if you have one-dimensional linearly dispersing states, you can calculate the density of states. You've done this as an undergrad or grad, you know. The density of states for one-dimensional linearly dispersing states is a constant. So that's what it is. What we are measuring here is that we have these linearly dispersing states that live in this channel, and because they are one-dimensional, you expect constant density of states, and that's what we are seeing here. Okay. And so that's really interesting. So you would think of this as a Majorana channel in your superconductor. The other thing is that you can do an energy dependence, and this is a spatial map, a DIDV map of the same states. So you can see at zero bias, they're pretty well confined. As you increase your energy, the spatial extent of the state increases. Right, at 0.75, which is somewhere here. Here's the coherence peak at larger than 1. It's pretty broad. At 1 millivolt right here, right, it's sort of completely spanned the gap. And so this is expected for topological states. As you increase the energy, as you get closer and closer to the band edge, the spatial extent of the state should increase and eventually completely span the gap. Okay, so that's it. I think that's all I wanted to show you. I'm sorry I hurried through this, but I really wanted to show you this data on FESCTE. What we find is that when you turn on a magnetic field, you have these really interesting zero bias bound states, which can be clearly distinguished from the regular Curly-de-Gennes states. And then if you are able to find this kind of a domain wall where the crystal has like a phase shift in real space. So this is like a phase shift, the two sides of the crystal are shifted in real space. That results in a pi phase shift in the superconducting order parameter. So at that boundary, you see states filling up the superconducting gap in this very uniform fashion. Okay, I'll stop here and take your questions.
Yeah, thanks for the talk. So I think yesterday you explained on how people make or tell you which kind of order parameter a superconductor has, depending on if you go through or if you look at the density of states, or like, we saw these shoulders and the...
Let me see if I can find that. Yeah, okay, I have it.
It's not too important, but then does one of these other things that you can put in the gap, like let it be like a Shiba state or a Majorana mode, do they also have these signatures of how the shoulders look and all of this?
So I'll show you very quickly what we do. So what we do is we look at the Fourier transform. Let me just show you what we do. Yeah, so we can see these. This is like quasi-particle interference, but it's Bogoliubov quasi-particle interference. So we park ourselves at the energy of the coherence peak and look at these kinds of scattering processes from here to here or from here to here. And we can actually look at the relative phase in the Fourier transform. We can look at the relative phase of the scattering process from here to here for one coherence peak and compare it with the scattering process for a different coherence peak. And that's how we get that it's S plus minus. Okay, so the analysis, the STM analysis is not very tricky, but the theory that tells you what to expect is not trivial. It was done by Peter Hirschfeld, and so I would say it's sort of involved. And so I would say one has to go through that whole thing to answer your question. How do you, yeah.
To be honest, now that I see it, I kind of mixed real and momentum space up in my head.
Yeah,
anyway,
yeah,
but,
exactly. Okay.
And
But you can see this in real space. It's actually really funny that you mentioned real space. You can actually see it in real space. These it's so hard to see here, but if you see, you can see all these waves. These waves, the pattern of these waves shifts in real space actually. So there's a real shift pattern you have waves, and if you look at one energy and another energy, the pattern is shifted by half.
okay.
That's the pi phase shift.
And did I only dream it, or did you promise data on uranium telluride yesterday?
I did, but there's no time. I don't know. I did, and actually, we have a lot of. So here I had the talk. I'll just show you the one slide, which is the most important slide on uranium ditelluride, and then you can.
I mean, I also saw your talk in Vancouver, but I wanted to ask then what Professor Dai showed with this anti-ferromagnetic fluctuations, but maybe we can discuss.
Yeah, we can talk later. Yeah, we can talk later. Sorry about that. In case someone's interested, you can ask me about this later. Yes.
Yeah, thanks for the nice talk. I guess it's very unlikely, but is there a chance that what you interpret as a domain was actually a 1D defect, like a dislocation or something?
Of course, the nice thing about STM is we can actually see the atoms. We can actually see that the structure on one side is shifted from the other by half a unit cell. And so when you say dislocation, right, so dislocations also have real space distortions. And so whatever dislocation you want to cook up, we can ask, what does that real space distortion, what is it supposed to look like? And so this is called a stacking fault. What I'm showing you is called a stacking fault. So it's really the crystal, as it's stacking, it just shifts a little bit. And so it happens during crystal growth. Dislocation is also interesting, and we have many different kinds of line defects in the system. And not all of them, by the way, show this. Only the ones where we have the lattice shifted by half a unit cell, only those show this. So just seeing a line defect is not enough, is what I'm trying to say. And those other line defects may be dislocations, for example. Yeah. We didn't pay attention to them because they were not interesting.
All right, thank you.
Yeah.
So as for this 1D chiral Majorana modes, so can you actually, so you show that the density of states is constant, but can you also show that they are chiral? I don't know, for example, can you place, I mean, that's my naive test would be that...
Sorry, I have to interrupt you for one second. They're helical.
Oh, so, okay. Okay, yeah.
There are two branches. Time reversal symmetry is not broken in this system.
Okay.
Yeah.
But, I mean, can you test that they're helical in some way? Like,
so you can ask, can we see, the only way we have an STM to look at dispersion is to do either quasi-particle interference or to do Landau level spectroscopy. I don't know if these things are supposed to scatter or not. I don't know if they're supposed to show interference patterns or not. So that's one way. I just don't know. Yeah?
In principle, they should get when you break time reversal symmetry.
Yeah. Do you want me to put a field in plane or out of plane?
I don't know. I haven't done this
Yeah.
calculation, but I would imagine that one of these directions should get, right? Should get the
I'd like to know if we should apply a field in plane or out of plane.
So out of plane is a completely different situation because it will change the phase difference as a function of position.
Correct.
So I wonder if a parallel field...
Yeah, so we're trying to get a magnet which can apply parallel fields, and next year we should be able to do these kinds of experiments. So that would be really interesting.
okay, thanks.
Have there also been shot noise measurements on this that could rule out Majoranas versus Cairoli de geometricon states?
Say that again, please. Say that again.
Have there also been short noise measurements of effective Fano factors that could rule out topology? effective Fano factor. That's something if you proportionality between, let's say, shot noise and current, and that can rule out the effective charge transferred per tunneling event, and that is sometimes used to distinguish trivial states versus Majorana states, also in STM.
Okay, I don't know about that, but short noises, huh?
It would be surprising if the short noise was different between the case of delta squared over E Fermi being 0 or being, nano-electron volt. I find it surprising that this could be, I don't know.
But the transport mechanism would be different, right? You get the perfect, what is it, mirror, the perfect Andreev reflection in the Majorana case. In other cases, you get, I don't know, a combination of Andreev reflection.
So short noise measurements require us to do a huge amount of work. We can't do it right now. We have to, probably put our preamplifiers inside the fridge, and we're not set up to do short noise measurements, actually. I think it would be really interesting. There are other predictions of short noise being used to distinguish between Maranas and trivial states, but we're not set up right now to do it. Yeah, unfortunately.
I tried it and bitterly failed, so I understand.
Okay.
Thanks.